Welcome to the deep dive. Today we're looking at a really interesting tension in the world of AI, something that researchers have been bumping up against for a while. It's this idea called the parameter performance paradox.
Right. The assumption for years has been pretty simple.
Ah.
If you want a model to do complex reasoning, math, logic, that kind of thing, you just have to make it bigger, more parameters.
But the goal now is to get these powerful models onto, say, a local device. And for that, you need them to be small, around 1 billion parameters, not trillions.
And that's the paradox. When you shrink them down, the reasoning ability usually just falls off a cliff. They get fast and cheap, but they're not nearly as smart.
So the intuitive next step, and the one most people would take, is to say, okay, if it can't be bigger, let's just give it more time to think.
Let it process longer. We see that with prompting techniques. But the paper we're digging into today, Think It Hard, found that when you build that idea directly into the architecture, it actually backfires.
It makes the model worse.
It can, yeah. The researchers looked at something called recurrent transformers, which is basically a way for the model to loop its own output back in to iterate on a thought before spitting out a word.
The idea being more loops, more thinking, equals a better answer.
That was the hope. They tested a version they called Always Think, where a 1.7 billion parameter model was forced to run 2 loops for every single token it generated.
And what happened?
Performance went down. It actually made more mistakes than the simpler model that only did 1 pass.
Which brings us to this core concept in the paper, latent overthinking. How can checking your work possibly lead to a worse result?
Well, it makes sense when you consider what language is actually made of. The paper points out that something like 85% of the words a model predicts are, for lack of a better term, easy.
Like the, and, or just finishing a common phrase.
Exactly. The kind of stuff a model gets right on the first try. So if you have the correct answer after 1 pass and then you force the model to process it again, you're not adding clarity, you're just adding noise.
You're corrupting a perfectly good signal.
That's a great way to put it. The model starts to second-guess itself. It essentially thinks its way out of the right answer and into a wrong one. That's latent overthinking.
So the problem isn't giving the model the ability to think harder. It's about getting it to stop thinking when it doesn't need to.
That is the entire premise of Think at Hard, or TI-H. They moved away from this rigid, always think twice model to something far more dynamic. The model has to learn to tell the difference between a hard token and an easy one.
Okay, so let's unpack the architecture that they built for this. It seems like there are a few key pieces. First, how does the model even decide what's hard in the first place?
They added a small separate component they called the iteration decider. It's just a lightweight neural network, an MLP, that sits on top of the main model.
And its only job is to, what, read the model's mind?
Sort of. After the first pass, it looks at the model's internal hidden states. It's essentially checking the model's confidence. It calculates what it calls a continuation probability.
And if that probability is high, it moves on. If it's low,
If it's below a certain threshold, in this case 0.9, the decider says, hold on, this looks tricky, and it triggers another iteration, another thinking loop. Otherwise, it just outputs the token.
it's a gatekeeper. Okay, but once that gate opens and the model goes into a second loop, the paper says just running the same process again is a bad idea.
Right, because the job has changed. The first pass is about predicting a token from context. The second pass, if it happens, is about refining a guess that was already deemed uncertain.
Prediction and refinement are different skills.
They are. So to handle this, they use low-rank adaptation, or LoRA. These are tiny adapter modules they slot into the model. And the crucial part is these adapters are only switched on when the model is in a deeper iteration, so depth 2 or more.
So the big base model is always focused on general language prediction.
Which is what it needs for those 85% of easy tokens. And then the LoRA adapters are like these little specialists that wake up only when a hard problem comes along. They're tuned specifically for refinement.
That seems really efficient. It keeps the model small. They mention less than 3% new parameters. But I see a potential timing problem. If one token takes 1 cycle to process, but the next token needs 3 cycles, doesn't that break the whole sequential flow that these models rely on?
It absolutely would. That's the challenge with parallel training on GPUs. You can't just have one part of the assembly line pause while the others keep going. It would be a nightmare for efficiency.
So how did they get around that?
With a really clever mechanism they call duo-causal attention. So a standard transformer model's attention works in one dimension, right? The sequence. A token looks back at the words that came before it.
Right.
Duo-causal attention adds a second dimension, depth.
So you can think of it like a grid, words going across and
Yeah.
thinking depth going down.
That's the perfect mental model. A token at, say, word number 5 and depth number 2 can look back at all the previous words, but it can also look at what those words were thinking at depth 1.
Ah, so it gets to see the whole thought process, not just the final answer from the previous step.
It maximizes the information flow. And because this is all structured as an attention mask, it can all be calculated in parallel during training. They get all the benefits of this complex dynamic thinking without the slowdown you'd normally expect.
Still, training a system like this sounds tricky. The paper mentions this coupling problem between the decider and the main model.
It's a classic chicken and egg problem. The decider learns by looking at the main model's states. But the decider's choices change how the main model behaves. If you try to train both at once, they can destabilize each other. The decider is aiming at a constantly moving target.
So they had to separate the training with something they call an oracle.
Yeah, the oracle is just a pre-computed perfect schedule. They took a reference model and figured out ahead of time exactly which tokens needed more thinking to be correct.
So they created the perfect answer key first.
Exactly. And in stage 1, they train the main model and its LoRA adapters using that perfect schedule. They force it to think hard on the right tokens and stop on the easy ones. This teaches the model how to refine its thoughts effectively.
And then in stage 2, they train the decider.
Right. They freeze the now trained main model, and then they train the decider to simply imitate the oracle. It learns to recognize the patterns that the oracle identified as being hard. It learns when to think deep.
So let's talk about the results. Did this whole complicated setup actually work? They tested it on some tough math and logic benchmarks.
It worked quite well on datasets like GSM-8K and Math 500. The TeraH model was about 4 to 5.4% more accurate than the standard single-pass models.
A solid improvement. But the really interesting comparison is against that always think model, the one that overthought everything.
And that's where you see the true value. TeraH outperformed always think by a huge margin, somewhere between 8 and 12%. It's definitive proof that just thinking more isn't the answer. Thinking smart is.
And it does this without a big computational hit, right?
The efficiency gains are a huge part of the story. Because it's only doing deep thinking on about 6% of tokens, its overall compute load, the FLOPs, is basically the same as the standard lightweight baseline model.
Whereas always think is just burning cycles.
3 to 4 times the compute, yeah, for a worse result.
I'm fascinated by that 6% number. What kind of tokens fall into that category? The paper actually analyzed what the model considers hard.
It did, and the results are so intuitive. The tokens that triggered the thinking loop most often were what you might call logic pivots. The number 1 token was but, which triggered a second thought 34% of the time it appeared.
And right behind it.
The word so at 18%.
So these are words that signal a change in direction in an argument, a contradiction, a conclusion.
A causal junction. The model instinctively knows, okay, a but is coming up. I'm about to introduce a constraint. I'd better double-check my logic. It's pausing at the most critical points of reasoning.
They included a great case study to show this in action. A really hard geometry problem about a heptagon from an old math Olympiad.
A great stress test. The standard model just got lost trying to define the coordinates and guessed a random number.
Incorrect.
And always think model, the overthinker. It actually set up the coordinates correctly, but then it got bogged down in the arithmetic. It overprocessed the calculation and came out with this bizarre fraction, 4320 over 17, also wrong.
The classic side of overthinking, finding complexity that isn't there.
Exactly. But the task model got it right. It paused to think harder when it was defining the geometric reflection points. And then it paused again when it was applying the final area formula. By only iterating at those key steps, it kept the logic intact and arrived at the correct answer, 588.
It preserved the signal, as you said earlier.
It did.
There's one last experiment in the paper that I think points to the future of this. They didn't just use the oracle for training. They also used it for testing.
Right. They wanted to see what the absolute ceiling for this architecture was. What if the decider was perfect? What if it never missed a hard token and never wasted time on an easy one?
And the results were pretty stunning.
On the math dataset, with the perfect oracle guiding it, the model's accuracy jumped by 25 to 28%.
28%. That is a massive leap from the 5% gain it gets with the decider it learned by itself.
And that's the key takeaway. It means the underlying model, with its LoRA adapters and special attention mechanism, is capable of so much more. The bottleneck isn't the engine, it's the driver.
The capacity to solve the problems is there. The model just doesn't always know when it's facing one.
That gap, the gap between the 5% gain from the learned decider and the 28% potential shown by the oracle, that's the room for improvement. The current decider is a simple MLP. It's good, but it's not perfect.
So it suggests that even these small models have this huge, untapped reservoir of reasoning power.
They do. And this research shows that maybe the next big breakthrough won't be about building an even bigger brain, but about building a better sense of self-awareness for the brain you already have.
A compelling idea.
Yeah.
Well, that covers the core findings of the Think at Heart paper. A fascinating look at moving from just more thinking to smarter thinking. Thanks for breaking this down for us.
My pleasure. It's really fascinating work.
We'll see you next time.